Alright, so we're going to work on the integumentary system today. That's basically, we're talking about the skin. A lot of people haven't heard that term, integumentary system, but that's what it is. It's the skin and all the accessory structures, our hair, our nails, and so on. The skin happens to be the largest organ in the body. Many people don't think of it as being an organ, but it is. There are lots of different tissues that we're going to go over with, and it's basically contains two layers. We have the epithelial tissue that we've already looked at, and then underneath that we have connective tissue. So we have looked at some of that connective tissue also. So the two layers, we have the epidermis and the dermis. And when we look at the epidermis, that is stratified squamous epithelium. It is a lot of layers. It's over 20 some layers of skin. And you can run your hand over like your hand and you can scrub off, several layers of skin and you still have plenty of stratified squamous left. Just FYI, buried in those layers are the protective bacteria that help to keep you from getting infections and that sort of thing. You'll probably hopefully learn that in AP2. But that epidermis, as we said, is composed of stratified squamous epithelium. So it has an apical edge, it has that basement membrane, and that basement membrane lays between the epidermis and the dermis. So that underneath that epidermis is the dermis. It is thicker than the epidermis. It is connective tissue. A lot of it is areolar connective tissue in this hypodermis. But it's connective tissue with collagen and elastic fibers, and that's where your blood vessels are, your nervous tissue. And below that, that lower layer is, beneath that is the hypodermis itself, which is areolar connective tissue and adipose tissue. It's not really considered part of the skin, but it does have a lot of the blood vessels. So we're looking here at that stratified layer. You can see it, nice smooth surface, and then the basement of that stratified squamous, and then we start to go into this dense irregular connective tissue, and below that, that adipose areolar connective tissue. So this is what the skin looks like in terms of a model. And you can see we're going to go through this. There are several layers to this epidermis, 5 layers, and then you can see this basement kind of uneven. It has what we call connected to these dermopapillae, and that is the top part of the dermis, and you can see that very thick dermis, and then undercutting that, the subcutaneous layer or the hypodermis. So that epidermis, again, stratified squamous. We do have several layers that we're going to go through. The uppermost layer is a stratum corneum, that very tightly packed cells going all the way down to the deepest layer, which is the stratum basale, or sometimes called the stratum germinativum, because that is the layer that is growing. That is, as we slough off these old cells, this stratum basale is the layer that actually grows new cells, and they migrate up. And as they migrate up, they die, and they gain keratin, which is a waterproof protein, and they become keratinocytes, and that process is keratinization, and it hardens those dead cells, dehydrates them, and that's what makes that tough outer surface that we have that's waterproof. Okay, we're going to talk about, there's some waterproofing that goes along with the oils and that are secreted on the skin. So those cells are evenly shed from the surface. They're very thick in the palms and the soles. Most of the body is much thinner, but obviously this epidermis makes us waterproof. I mean, you can sit all day in water and you won't melt. So it prevents water loss. It prevents harmful chemicals. You can stick your hand in certain things that could be harmful, and it's not going to eat in unless it's very, very corrosive. It protects us from getting injured, And it also protects us from these pathogens. Again, you have these bacteria that are in those layers of that skin, and they are very protective. They protect their territory, and they will kill invading organisms, invading pathogens. So if we take a look at the layers, here are the layers from the outermost layer to the deepest layer of that epidermis. The stratum corneum, this stratum lucidium, and that's only in thick skin, stratum granulosum, the stratum spinosum, and the stratum basale, or again, sometimes called in some textbooks the stratum germinativum. And you can see that they change a little bit in characteristic. And the granulosum is about 3 to 5 layers thick. The spinosum has little spicules, and that's why it's called the spinosum. And then we finally end up with the stratum basale, which is a single row of cuboidal or columnar cells, and that is your dividing layer. And that's the layer that also has the melanocytes to give you the skin color. So you can see them very clearly all separated out here. All right, so your corneum, your lucidium, your granulosum, and on down. This is just a real nice look at this. All right, special cells that you're going to see in the epidermis, dendritic cells or Langerhans cells. Do not confuse dendritic cells with dendrites. You know, we studied with the nervous tissue those dendrites that carry the nervous conduction to that, axon away, dendrite to. So you're taking that information into the cell so it can be passed on. Those are nervous tissue cells. Dendritic cells are really immune cells. So don't get the two confused. They are phagocytes. We talked about phagocytosis before. So these guys are going to go and eat any kind of thing, if you will, that was come invading or organism or some debris and clear that away. You also have your tips of your skin, especially your fingertips in certain areas, but all the tops of your skin is very, very sensitive. You have a lot of nerve endings there. If you blow on your arm, you can feel that air. You touch with your fingertips, very, very sensitive. You have these tactile cells that are found in the skin. One of them is called the Merkel cells. They are sensory receptors for light touch. You also have the melanocytes. This is also in the stratum basale. This is going to produce the pigment melanin, and that is how you get the color into your skin. And then obviously that is determined by the genetics that you have. And these cells absorb the UV light and provide skin color. And it protects us from UV radiation. So you can take a look at this dendritic cell and one of these little tactile cells. The different skin color comes from a couple different pigments, and you can take a look at that, and they are found in different areas. And again, all people have the same number of melanocytes, but they vary in the amount of melanin that is produced. And again, that is under genetic control. There's basically about 9 genes that help determine the basic colors, and there's a lot of variation in the distribution and the size of these granules. If you lack these genes, then you are albino, okay, and you don't have that melanin. So several factors in terms of environmental factors for skin color. Amount of sunlight. Those of us that live in the south are obviously a lot more tan than those that live in the polar regions. If you do any UV sun tanning under the sunlight lamps, or you're exposed to certain radiation. Other physical factors, the amount of oxygenation in the blood. If the oxygen level is low, you can become cyanotic. If it's really high, you can become pinkish. If you get carbon monoxide poisoning, your skin gets really, really, really red, cherry red. So it all depends on what's going on. Also, the dilation or constriction of blood vessels. Obviously, you constrict the blood vessels, you get pale, you dilate them, you get flushed. You can also get a little bit of an orange tinge to your skin from diet if you eat too much carotene, particularly like carrots. And another one is jaundice. Jaundice is formed because of the breakdown products of blood, that bile, and it will give your skin a yellowish cast. So I gave you this little clinical application, indoor tanning and skin cancer, and just FYI, you do get doses of UV radiation that can overwhelm that response by the body to normally clear out the cancer. And basal cell carcinoma, squamous cell carcinoma come from the epithelial cells, the basal layer. Okay, so basal cell carcinoma, the most common skin cancer that we have, and generally very, very curable, but melanomas arise from the melanocytes, and this is the least common of the skin cancers, but cause a lot of cancer deaths. Okay. All right, so we move a layer down, and we go into the dermis. So this is usually not very, very, very thick, 1 to 2 millimeters thick. It does contain those projections I showed that are called the dermal papillae that lay between these ridges, and that binds that epidermis to this layer. This layer, it's a connective tissue layer. It does contain some nerve cell processes, that you do have blood vessels that are supplying nutrients. It contains the hair follicles, our sweat glands, our sebaceous glands that we're going to look at, and there's also a lot of these sensory receptors in this area. The laminated corpuscles, what we call Pacinian corpuscles for pressure, and those tactile corpuscles for light touch that we'll take a look at a little bit later on. So the dermis is 2 layers, the papillary layer and the reticular layer. The papillary layer is the more superficial. This is areolar connective tissue, and it lays in the dermal papillae, which form our fingerprints. And then you have the deeper layer, which is dense irregular connective tissue, which is, again, a little bit layered down. All right, the sebaceous glands, some of the glands we look at, sebaceous glands are what we call holocrine glands. They're made, a holocrine gland by definition is something that, a gland that is made up of these products, the secretory products that are formed inside the cell, and then they're released when the plasma membrane of that cell ruptures. It's usually associated with hair follicles. The secretory product that is produced is called sebum, and that is a fatty cellular debris, but it helps keep our hair and our skin soft and waterproof. And an excess of this is what causes you to get acne. And it is not found on our palms and our soles of our feet. So, and you can see that little hair follicle here and those sebaceous glands there. So acne is a disorder of these sebaceous glands. It's very common at puberty, and you're just producing, excessive amounts due to the sex hormones being produced, starting to be produced, and the glands become clogged, and that is a good environment for anaerobic bacteria to grow. Again, an anaerobic bacteria is a bacteria that doesn't have to have oxygen, so it's a perfect growing environment for anaerobic bacteria. And a lot of people in their teenage years through their 20s are affected with this. And you may be one of those. All right, so then we get into the sweat glands, sedophorous glands. We have these widespread over the skin. This becomes very important because this is sweat. This has salt in it. and you lick your hand or whatever, you'll taste a little bit of that salt. What that salt does really is it is antibacterial. It is antimicrobial. So, and if you get a bacteria or a microbe on your skin, it will generally take care of it, because bacteria don't like that high salt environment. Basically, you have a few types of sweat glands. The acrican glands or the Merkel glands. These are the most numerous. They are mainly water and some salts, and they respond to elevated body temperatures. So you get hot and you sweat, those pores open up and they go directly to the surface, and you just get the beads of sweat on your arms or legs or wherever. The acrican glands, these are sweat glands also, but these are primarily in the axillary, the armpit area, or the groin. This opens instead into hair follicles, and these respond to emotions and to pain. And then we have a couple of specialized sweat glands, ceruminous glands, that we'll look at a little bit later on when we get to the ear. But these are the glands that sit at the external canal of the ear and secrete the earwax. And then we have the mammary glands, which are a specialized sweat gland that secretes milk. So you can take a look at the Merkel sweat gland and acrican sweat gland. That's a little bit closer down in there towards the fat layer. So some of the functions of the skin, as I mentioned, it's a protective barrier. It protects against harmful substances, water loss, these microorganisms, as I talked about. We have a lot of sensation with our skin. They are touch receptors, pressure receptors, there's temperature changes, pain receptors. So the skin gives us a whole lot of information. We can excrete some waste through the skin. Another big thing with it is production of vitamin D. It actually starts in the skin, and when it's activated, it does help with calcium absorption. So you want to get out in the sun a little bit. You just don't want to get out too much. And then obviously, as we talked about, there's regulation of body temperature. We cool the body by sweating, and we'll talk about that. And we cool the body or heat the body by doing dilating blood vessels or constricting blood vessels. Okay, so if we look at this heat loss and production, this is important to the body temperature regulation. Again, we are warm-blooded mammals. We have to have a fairly consistent body temperature. We get too cold, enzymes don't like it. We get too hot, we denature. We have a very small area of operating temperature, if you will. So it's important that we regulate this body temperature, because just slight shifts in those temperatures can really disrupt metabolic reactions that we have. The set point for a temperature is monitored in the brain in an area called the hypothalamus that we'll be looking at a little bit later on. But the deep body temperature stays close to that set point of 37 degrees Celsius or 98.6 degrees Fahrenheit. The skin is going to be a different temperature depending upon what the environmental temperature is. But the idea is to keep the deep body temperature at that 37 degrees. So the skin plays a very key role in that mechanism of maintaining homeostasis to regulate the body temperature. Heat is produced in cellular metabolism. We just talked about that with the metabolism chapter. And it is produced by the most active cells, like our muscles, our skeletal muscles, our cardiac muscles. Most of us know that if we exercise, those, our arms and our legs get warm and they sweat. It's the heat that's being produced. There are several different ways we can lose heat. One is by radiation. This is our primary method. And basically, if the heat goes from the warmer skin to the cooler environment. It just kind of moves. It's, if you sit there and think about, you go to bed, you put a blanket on you, and for some reason all of a sudden you go from cooler to warmer, and that's just the heat that's radiated off your skin. All right. You can do conduction, which is the heat moves from the warmer skin to a cooler object. You sit there and you touch like your cup of coffee or something which you are maybe whatever you may be touching, a utensil, a fork, a spoon, and that's cold initially, but once you start to hold it longer, then those warm up, and then the heat from your skin is just being conducted onto that object. All right, and then we have the heat loss from the circulating air currents, that's convection. And then we have evaporation, which is lost through the sweat. As we sweat, it will evaporate and it will carry it away from the skin. That is why when the dew point in the environment, the humidity is lower, we evaporate quicker. And when the humidity is high, it's harder for us to evaporate that water, and that's why we feel the heat so much more. Okay, so the body temperature regulations. When the body temperature rises, we have the receptors are telling the hypothalamus that the temperature is rising, and what will happen is we will vasodilate, we will expand those blood vessels in the dermal layer, and we will constrict the vessels in the deep blood vessels, and the sweat glands get activated and we start sweating. When the body temperature falls, we get the same signal from the thermoreceptors, but we do the exact opposite in terms of the response. We vasoconstrict the dermal blood vessels. We move the blood into the core of the body, which is why if it's a seriously cold temperature, you can get frostbite on your nose and your ears and your toes and your feet. And your fingertips, and that is because we are moving all that blood into the core of the body. The sweat glands are inactive. We don't want to lose heat, and we start to shiver, and we know that by shivering, the muscles are going to produce heat. Some of the problems that we run into: hyperthermia. This is when we have a really high body temperature, usually above 105. This can occur on a hot, humid day. You can have some serious heat exhaustion or heat stroke. And basically what happens, you can't sweat too well because you can't evaporate. As I talked about, the humidity is too high and you just can't evaporate. And if you can't evaporate that sweat, you can't cool the temperature. And the body can gain heat from the hotter air, and the person becomes weak and dizzy and nauseous and a very rapid pulse, and heat exhaustion, very weak. Heat stroke can be very serious. Hypothermia, basically prolonged exposure to cold or something like that, and you do start to shiver involuntarily. And it will progress to confusion and lethargy, and there's been plenty of times you just don't know where you are, and people have walked out in the snow completely nude and die because they're so confused. It just happens to happen. And without treatment, the organs do begin to shut down because our enzymes just won't work at that low temperature, so we are no longer able to do any metabolism. Okay, clinical application, fever, the set point. Basically, when you get a fever, a lot of these organisms will be detected like a bacteria or something like that, and the phagocytes of our body will go and eat these guys, if you will. They will phagocytize them, and they will release pyrogens. And these pyrogens raise our set point. The reason why we want to raise our set point is that bacteria that live in our body that are and that are pathogens to us, like our body temperature. If you raise the body temperature, you have a good chance of killing them. So this is an automatic response that happens, and the hypothalamus increases the set point to raise that body temperature and hopefully help destroy those pathogens. Okay, so in terms of the skin and what happens, what's interesting is when you get a skin wound, when you get a burn, you're going to see a certain response, and that is called an inflammatory response. This is a normal response. A lot of times people think the word inflammation, they think it's bad. But an inflammatory response is a normal response to injury or stress, and it's the body's attempt to restrict that spread of infection. So what happens is the blood vessels in the infected area dilate, they become more permeable, there are white cells, we'll talk in AP2, that actually move out of the blood vessels and go into the surrounding tissues, into the damaged tissues. And basically what we're doing is leaking the fluids and the cells into that damaged tissue. Well, because of that, because you're dilating these blood vessels, the skin gets red, the skin swells from the increased amount of fluids. You've got increased blood flow to the area. Blood is warmer than skin, so it gets warm. And then you're getting these pressure sensors saying, I got a lot of pressure against me. And so it's becoming painful. That you should see a little, if you cut yourself, you should see some of this response. This is normal, okay? So a shallow cut that only affects the epidermis, this is going to be very easily filled in and taken care of. A deep cut is a different story. First of all, we have to stop the blood loss. And we've got to form a clot. That clot is, and you'll learn this in AP2, consists of fibrin and blood cells, and the platelets, the clotting cells that we learned about. And they will clot and form a scab, and then the epithelial cells will reproduce and fill in that wound. And then we will have collagen kind of bind everything together, and there are certain things called growth factors that will stimulate the new tissue to form. Right? And you will have cells that will come in and remove the dead cells and remove the debris, and the scab sloughs off. And you may or may not have a scar depending upon how bad the whole situation is and how deep this is. Okay. With burns, it's obviously an issue in terms of how deep this is. Burns are classified according to how extensive the damage is. You can have superficial burns, you can have deep burns, but we're going to go through these different degrees, and the reason we do this is because this tells us what we got to do to treat these burns. So you may have a superficial partial thickness burn, which is what we call first degree burn. This is usually only the epidermis. You went out and you got sunburn, not too bad a sunburn. You turn a little red, it gets a little warm, it's a little inflamed, and a few days later you're okay and everything goes away. You can get a deep partial thickness burn, which is a second degree burn, and this is where the epidermis is destroyed and it gets down into some of the dermis. So you get burned from a hot liquid, or you really stay out in the sun all day, or something like that, and you may blister. I've seen a lot of people with some really bad sunburns, all blistered up, and it will depend on the severity of the burn there. And it usually can regenerate skin, you usually recover, you usually don't have any scarring. If you go to a third degree burn, a full thickness burn, this is a little different. This destroys the epidermis, the dermis, all the accessory structures. You get, usually this is, you got seriously burned in exposure to flames or heat, or you got, scalding liquids, or you got it, unfortunately, into a burning building or something like that. Depending upon how much of the skin is exposed and burned will determine whether you need a skin graft. You may get a skin substitute, you may get a graft. It really depends on how much and how deep these burns are, what treatment's required. So what we do is we use what's called the rule of nines, and this divides the body surface into regions of 9%, and it's used for the estimate of what amount of surface has been burned. You'll hear them, they're burned over 70% of the body. Well, how did they get this? They got it through what we call the rule of nines. And this allows us to plan replacement fluids, plan electrolytes, trying to figure out what to do. So you can take a look at this rule of 9, and you can see it depends on what it is. And generally, if you've got a 3rd degree burn, that's a tough one, and you may need a skin graft. All right, so that's it for the skin, and we'll see you on the next chapter.